Welcome to our work. I'm Zhi Yuji, and the other three authors are Xiaodong Yang, Zhuang Ma, and Zhe Ren. We are from QCraft. It's my great honor to introduce our paper, GEDepth Grounding Embedding for Monocular Depth Estimation. Monocular depth estimation is inherently ill-posed. Although recent supervised methods like depth-former, pixformer have achieved remarkable progress, they are still tailored toward the specific compound or pictorial clues and camera parameters on a particular training data. In light of the above observations, we think that if we can find a way to figure out the depth or the approximate depth of part of the image, it should be helpful to alleviate the uncertainty in this task. Ground plane is a very common clue in real-world application, like autonomous driving. Our work focuses on this part. Left figure shows that we can map each pixel into an array, and if we know the mathematical formulation of ground plane, we can compute the depth for each pixel. In the right figure, top demonstrates the ground depth calculated from camera parameters. Bottom visualizes the pixels of which ground depth value are sufficiently close to the sparse ground depth values provided by LiDAR. For the ideal planar ground, if the height of a planar ground is known, we can calculate the accurate depth for ground area in a closed form solution, derived from the pinhole camera model. The transformation between a point in the world coordinate system and its projection UV in the pixel coordinate system can be described as the first equation in the first row. After some simple transformation, we can get equation 1. Since we know the height of planar ground, we can get equation 2 easily. By combining the equation 1 and equation 2, we obtain the ground depth value of pixel UV as equation 3. For the undulated ground, we denote point O as the projection of camera optical center to the ideal planar ground, and then connect O with every surface point. For each image pixel UV corresponding to the surface point of undulated ground, we define the ground slope as the angle alpha between ideal planar ground and the projection of collecting line on the YZ plane. We can extend the ground description from the ideal planar ground into the undulated as equation 2. Equation 1 is the same as we have already mentioned. By combining equation 1 and equation 2, we obtain the ground depth value of pixel UV as the equation 3, where only the ground slope value alpha is unknown. In practice, by leveraging the available ground depth value of sparse ground surface point, we can transform equation 3 to equation 4 to provide sparse distribution of ground slope in order to facilitate the ground slope map learning. Here's an overview of our proposed ground embedding module integrated in a typical depth estimation network. Given camera parameters, we compute the ground depth and stack it with the input image to produce the depth-aware features through the encoder. A ground attention block is developed to selectively combine the ground depth and the residual depth to form the final depth estimation. In the vanilla mode, the computation of planar ground depth involves camera parameters only, while in the adaptive mode, a ground slope block is additionally used to deal with undulating. This figure shows the visualization of ground attention maps and the ground slope maps of the two things in the test set of Kitty. It's noteworthy that the ground attention map is totally learned implicitly without using extra supervision provided from additional models as ground segmentation. We show the comparison of GEDepth in both vanilla and adaptive modes, and the state-of-the-art methods on Kitty in this table. Groups 2 to 5 correspond to the 4 representative methods integrated with proposed ground embedding module. This shows that our mod method is helpful for both CNN-based method and transformer-based method. We achieved the state-of-the-art on Kitty by adding GE plugin into depth-former. We also do experiments on DDAD, and we get the consistent gain like Kitty. In addition to state-of-the-art accuracy, our method also shows great generalization enhancement in a lot of aspects. That figure compares the relative improvements over the two methods under different distance intervals on Kitty. Though it is observed that as the distance increases, GEDepth vanilla and GEDepth adaptive both provide notable performance gain. As compared in the right figure, depth-former and BTS are both very sensitive to the change of image resolution. In the contrary, GEDepth adaptive makes the two methods substantially more resistant to the resolution change. As shown in the left figure, depth-former and BTS are both tremendously degrade when they transfer from the forward to the other views. As a contrast, GEDepth adaptive largely improves their view transforming performance. As shown in the right table, we further train the network on one dataset and then evaluate on the other without fine-tuning. Compared to the depth-former, GEDepth adaptive improves the result by a large margin on either way, revealing that our ground embedding is more robust to the change of data distribution in addition to the change of camera parameters. We, in the end, take a closer look into impact of our approach to network inference latency, which is an equally important property for a lightweight plug-in module. As can be seen in the table, GEDepth remarkably improves the performance, but with a small increase in the network parameters and inference latency. Thank you for listening.